Good afternoon, everyone. I am Rajat from Department of ECE, RV College of Engineering, Bangalore. The title of my paper is Approximate Multiplier for Power Efficient Multimedia Application, paper ID 327. So these are the contents covered in this slide, starting from the abstract, then introduction, literature review, then exact and proposed multiplier, their methodology, result analysis, and finally conclusion and future work. So in recent times, the design of fast integrated circuits with less power consumption has become important as technology advantages and chip dimension are reduced to enable circuit with low energy consumption. This paper proposes an approximate multiplier design based on a dual stage 4:2 compressor multiplier with high speed and low power consumption. The compressor proposed are used to implement the 16 cross 16 data multiplier. The proposed circuit provides a better balance of hardware and accuracy metrics. The design is simulated using Vivado Arctic 7 technology. The necessity of approximate multiplier has paved the way for rapid computing in error-tolerant applications, for example, signal processing and multimedia. So, approximate computing is a novel method in digital design that minimizes the requirement for exact calculation to gain considerable power, speed, and area advantages. Its application can be in the field of multimedia processing, image multiplication, and machine learning. Multipliers are essential components in microprocessor, DSP, and embedded system and have a variety of uses, including filtering and neural networks. But due to advanced logic architecture, multipliers are one of the most power-hungry digital components. Therefore, approximate multiplier design has become an important research topic in recent years. So multiplication involves mainly three steps, that is partial product generation, partial product reduction, and final addition. Approximation can be added in any of these steps. So the block, so exact multiplier methodology. The block architecture of an exact first to two compressor is shown here. It comprises of 5 inputs, 3 output, and 2 cascaded full adders. X1, X2, X3, X4, and Cin are the inputs. Cout, carry, and some are the outputs of the exact first to two compressors. The equations are listed here. The disadvantage of this method is power consumption is more and area efficiency is less. A 4:2 compressor is used to shorten the latency of the parallel multiplier partial product summation stage. The compressor has 4 equal weighted inputs M1, M2, M3, and M4, and input carry Cin as well as 2 outputs sum and carry, and output Cout. The output sum is the same weight as the input, but carry and Cout have double the weights. And this paper proposes two novel architecture for the compressors. One is high-speed area-efficient 4:2 compressor, and the other one is modified dual-stage compressor. The proposed high-speed area-efficient 4:2 approximate compressor is shown here in Figure 5. The compressor input are A1, A2, A3, A4. Output are sum and carry. A multiplexer-based design approach is used to generate sum and sum. Output of XOR gate acts as the select line for the mux. When the select line goes high, A3, A4 is selected, and when it goes low, A3 plus A4 is selected. Based on this, the sum and carry equations are listed here. The second compressor is 4:2 dual stage compressor. In this, OR and AND gates each need 6 transistors in CMOS logic implementation. In order to reduce the transistor count, this paper proposes an architecture with NAND and NOR gates. These blocks are developed using Vivado software. So here we can see 9 cells and 12 nets are required for the dual stage, whereas 8 cells and 11 nets are required for high speed 4:2 compressor. These two compressors will give approximate results. For exact result, we have to use exact compressor, which will need 11 cells and 15 nets. So this is a comparison table that what I explained in the previous slide. So we can conclude the proposed design are more area and power efficient. The high speed compressor block takes minimum number of cells and nets compared to dual stage, and the analysis is done using Vivado. For comparing the device utilization and power consumption of both the design, and 8 cross 8 bit data multiplier tested in both designs, that is with only high speed 4:2 compressor and with only dual stage compressor. The simulation and synthesis are done using Vivado. Now coming to exact multiplication design. So this is the RTL schematic for exact multiplier. Here we can see 405 cells and 675 nets are required, which is very complex. So, and this is the waveform generated. So here we can see if we multiply 420 with 5267, we'll get exact this result. Similarly for other. So now coming to proposed multiplier. This is the proposed 4:2 compressor based 16 cross 16 multiplier. Here for the LSBs we are using high speed area efficient compressors. For the middle bits we are using modified dual stage compressor, and for the maximum MSBs, most significant bits, we are using exact compressors because they will contribute most to the final result. So we want to reduce the error. So for MSPs, we are using exact compressors. So this is the RTA schematics of the proposed multiplier. Here we can see the cells are reduced from 405 to 140 cells, and the nets are also reduced from 675 to 596. This is the proposed waveform proposed multiplier waveform. Here we can see if we multiply these two numbers, the result. This is the result obtained, which is very close to the exact result. The error with this multiplier is less than 1%. Now coming to the area utilization report, this is the report for the existing model, power area utilization report. Here we can see the slice LUTs are reduced from 421 to 285 in the proposed model. Now coming to the power report, the on-chip power is 38.867 watts for the existing model, which is reduced to 33.056 watt for the proposed model. For the timing report, the data path delay is 17.185 nanoseconds, the maximum data path delay for the existing model, whereas for the proposed model, the data path delay is reduced to 15.417 nanoseconds. This table 3 displays the component distribution used to synthesize the exact and approximate multiplier. The exact multiplier is significantly more complicated and requires more LUTs. The proposed multiplier reduces total on-chip power, LUT count, and latency. Now the conclusion: high-speed, area-efficient compressor architecture is designed and evaluated in terms of delay to modify and a modified dual stage compressor without affecting the accuracy metrics of an 8-bit multiplier. When compared to the 8-bit multiplier, a 16-bit multiplier design using a mix of both the approximate compressor design and exact multiplier yielded a significant reduction in area, latency, and power. Now, the future works involve developing an approximate multiplier that can be enhanced further to reduce delay and power usage, since the area reductions are obtained at the expense of greater power usage and an increased critical path delay. These are some of the references. Thank you.